Hi everybody, thanks for coming. It's a great turnout. I'm really excited to be here. Believe it or not, this is the first time I've ever been to the Exploratorium. It's a fabulous place and I'm really enjoying myself. So great to be here. So as Nicole said, we're celebrating the 25th anniversary of Hubble this year. In fact, just a couple of weeks ago was the 25th anniversary of the launch of the Hubble Space Telescope. And I'm going to try to tell you about how we get these pictures, how we make the pictures, and what goes into it. So if you've been looking at the slideshow here, you've seen a lot of them. I'll go through a couple and then we'll talk about how they come to be. So we start out similar to if you were here for the previous talk, hearing about remote sensing, remote photography of our solar system, planets in our solar system. It's a great presentation. Hubble is another kind of remote sensing, but instead of traveling to these places, Hubble is in orbit around the Earth and looking out at the sky all the time. And we're looking at things in our solar system like Jupiter here, like Saturn. If you watch carefully, you can even see the moons going across Saturn. There's Titan. We saw some pictures of Titan earlier. Really close-up pictures. This is with Hubble. And we can look at the planets for a long time over repeatedly and watch the moons travel across there. So as we go farther out, we're seeing stars in our galaxy. We can go out at night if you go to a nice dark site and see stars in the sky. Hubble's sky is dark all the time, so we're seeing all the stars in their great glory. This is a cluster of stars that are bound by their own gravity. We're seeing a very dense field of stars here with great color separation, and I'll talk about those colors in a little while. As we go farther out, we see all kinds of unusual phenomena with Hubble. This is a particularly interesting thing called a light echo. I don't have time to go into all the details about all these objects, but you can learn about all this stuff online. There's some amazing things going on out there, and Hubble sees it in great detail. It's another thing, there's a famous object in the sky called the Horsehead Nebula. It's been photographed by just about every telescope, amateur and professional that's able to take pictures through a telescope. It's a very famous object. Hubble took this picture in infrared light, not in light that we can see, but in light that's redder than the reddest light that we can see, infrared light. And then going farther out, we also see places where there's new stars being formed. This is a giant area of gas and dust where stars are being formed deep within these structures. We also see stars die. This is something called a planetary nebula. It doesn't have anything to do with planets. That's a historical term. But this is a phenomenon where a star has shed its outer material into the space around it, and the remnant star is illuminating that gas around it and causing it to glow. And another more violent death of a star is a supernova. This is a famous supernova remnant called the Crab Nebula for kind of obvious reasons. It kind of looks crab-like, at least in a smaller telescope. But this is a star that's completely blown itself apart, or almost completely blown itself apart, and all that material is now scattered out in space around it and is caused to glow. Then much farther out, outside of our galaxy, we see many other galaxies out there. This is just one example. Happens to be one of my favorite galaxies, one of my favorite Hubble pictures, is a beautiful barred spiral galaxy. Spiral because it has these elegant spiral arms. Barred because it has this straight structure running down the middle that's called a bar. And then other kinds of galaxies, these are galaxies that are interacting with each other. Their mutual gravity is actually tearing them apart and causing them to be distorted in all kinds of weird shapes. Hubble has observed hundreds of these kind of interacting galaxies and has led to a better understanding of how that interaction happens and what happens to those galaxies. Much farther out, this is probably one of the most important pictures that Hubble has taken. This is essentially a picture not of the entire universe, but a kind of core sample of the universe, looking at a very small spot in the sky, but to very, very great distances. All these objects are very faint. Almost every object you see in this picture is a galaxy that's as big as our galaxy, but much, much farther away. And it's these pictures that Hubble has taken is allowing astronomers to understand the structure of the universe as a whole and what's happening to the universe and what has happened to the universe in the very, very distant past. And then even farther out, Hubble can use a quirk of, or astronomers can use a quirk of physics that light is bent around a mass, and because of that bending, that light can get focused just like a glass lens can focus light. And just as a glass lens can concentrate and magnify images and magnify the light of very distant galaxies gets magnified, distorted, and amplified by the mass in this cluster of galaxies, and therefore allows us to look even deeper into the universe than we could without that intervening mass in the way. If you're familiar with Hubble pictures, you may have seen this picture before. It's one of the most reproduced, most famous images from Hubble. Astronomers call it M16 or the Eagle Nebula, but it's also become popularly known as the Pillars of Creation. Creation because stars are forming within these pillars, and pillars for obvious reasons because they look like pillars, and they are, in fact, are pillars of gas and dust. Now this picture was taken in 1995, roughly 20 years ago, by a previous generation of instrumentation on Hubble Space Telescope with a camera called Wide Field Planetary Camera 2, or popularly known as WFPIC 2 to the astronomical community. So just a few months ago, just last year, we took the same part of the sky with the newest instrumentation on the telescope, a camera called Wide Field Camera 3, the follow-on to Wide Field Planetary Camera 2. So this is the next generation of detectors on the telescope. As you know, cameras get better all the time, electronics gets more advanced all the time, and astronauts have visited Hubble and have serviced it and been able to keep the telescope up to date with the latest in technology. So with that latest technology, we produced a new version of this picture, which we now see here. So we got a wider field, we get better resolution, which you can't necessarily see at this reproduction size, but if you look very closely, and in fact I can zoom up on this, we actually get much better detail in this image, much higher contrast and lower noise than we did in with the previous generation of camera. Now the other advance that's happened with Hubble's instrumentation is that this image was taken in visible light, but the Wide Field Camera 3 is actually two cameras in one. It's a camera that takes images in light that we can see. It also takes images in light, in infrared light, which we cannot see. So this image was taken, this exact same region, in infrared light. So as you see, a lot of that nebulosity, a lot of that structure more or less disappears, and in its place we see a whole bunch of stars. And we now see those stars because the infrared light is not being blocked by that material, whereas the visible light is blocked. The visible light from those stars is blocked by that gas and dust, but the infrared light shines straight through it. So we can see a lot more through that with the other camera, and that's why that camera was built and installed, so we can take pictures, see different kinds of things and observe different kinds of things in different kinds of light. So where do these pictures come from? It's photography. We're talking about photography here, all kinds of really cool, fascinating stuff about photography here tonight. So how does Hubble photography differ from the kind of photography you might be used to taking it with a regular camera or your cell phone camera? Well, we'll do a little compare and contrast. So it's similar in many ways. It's photography, it's recording light, recording intensities of light, but it's really quite different also. So whereas the photography you're used to is used for all kinds of different things, whether it's journalism or for producing art photographs or wedding photographs or whatever, Hubble's photography is very, very specific. We are looking at the sky. We're looking at very faint light from very distant objects. And that's all that Hubble can do. Now there's a whole universe out there to look at, so we have no shortage of things to look at, but we can't take wedding photographs with Hubble. So we only a very narrow niche of kind of photography that we can do. And of course the telescope was built to do science. It wasn't really made to make pretty pictures. Fortunately, the images lend themselves to making pretty pictures, and I think of them as a byproduct of the science. And we use these images, the images that we produce, the color images that you see in the slideshow here and that I showed first of all, they're not really used for science as such. The scientists take the data, the raw images basically, and analyze that to figure out what's going on there. We produce these color pictures partly because we can, and they're cool. But we also use them to teach, to show what Hubble is doing. And that's the primary purpose of making these images. So what kind of things are we looking at? As I said, with a normal camera, you can take a picture of anything, right? Hubble only takes pictures of the deep sky, very faint light coming from the sky. What kind of equipment do we have? Well, standard cameras are very, very versatile. You can change, on that kind of camera, on a single lens reflex camera, you can change the lens, put a wide angle lens on it, get a nice landscape view, put a telephoto lens on it and take pictures of wildlife. You can take very close-up pictures, all kinds of stuff. With Hubble, we're much more constrained. We have a fixed focus lens. We don't have a zoom lens. We can't change the aperture. None of those things you can control with a normal camera. So it's extremely specialized, and it's designed to do science. It's designed to take the kind of pictures that scientists want to take to analyze their pictures. So the final thing is how the images get captured. So a normal camera produces color images automatically, and that's done on the sensor inside the camera. It divides the light up into component colors, and the camera puts those colors back together and spits out a nice color image that you can download on your computer or post on Facebook or whatever. Hubble, on the other hand, only takes black and white pictures. So that color separation happens within the camera, but the camera doesn't put those color pictures back together. That's where I come in, that's where my team comes in, and we put those images back together. So what makes Hubble so special? Hubble is pretty special. We've been seeing these pictures for now 25 years. We've been hearing all kinds of results that Hubble has advanced astronomy, has rewritten textbooks over and over again. What makes it so powerful? Well, for one thing, it's a normal research telescope, very powerful telescope. It turns out that it's actually not as big and powerful as many telescopes on the ground. It's really hard and really expensive to launch big things into orbit. So we couldn't launch as big a telescope as we can build on the ground. However, it is still a very capable telescope for research purposes. It has a full complement of science instruments, just like a normal observatory on the ground would have. Different kinds of instruments to do different kinds of science. It's an observatory, it's not just a telescope. It's also has been able to be serviced. The shuttle, astronauts on the shuttle were able to visit Hubble and fix things that broke, put new technology in. As I said, technology advances every year. So we've been able to put the latest and greatest technology into Hubble, and it's now operating as well or better than it's ever operated before. So that's what's really kept it going for the 25 years, the ability to fix it and to upgrade it periodically. But the big thing, there's one thing that Hubble has that no other telescope, just about no other telescope has, and that's it sits above the atmosphere. Now sitting here on the ground, we have to look through the atmosphere if we want to look at the sky, day or night. So as you know, if you go out here at night, the sky is very bright because of all the illumination around. Even if you go out to a very dark site, up to Yosemite, the sky still has brightness. Not only that, the atmosphere, the air itself, the air is moving around and causing the light to be distorted and absorbed that's coming from the sky. So that's why Hubble is above the atmosphere. Hubble is in orbit, 300 some miles above the Earth, orbiting every 97 minutes. And so it doesn't have that nasty atmosphere to have to look through. So that's why the images are much sharper, much darker background, so we can see much fainter light sources above that background. That's what makes Hubble so powerful. So where do the images come from? Well, photographers always like to talk about their equipment. This is the equipment that we have. This is one of the primary cameras on board the telescope. This is the Wide Field Camera 3. I showed some pictures made with the Wide Field Camera 3. It's actually two cameras in one, a camera that looks at visible light, a camera that looks at infrared light. And this here on the right is the actual detector. You can see roughly how big it is. You know, it's maybe an inch, inch and a half square, 16 megapixels. So that's a pretty respectable camera by modern standards. There are larger consumer cameras that you can buy consumer cameras that have more pixels in them. These are very specialized detectors that can see light very faint. They have very good noise characteristics, so they don't produce a lot of noise when you're looking at very faint objects, and they're very precise. So the other feature of these cameras is that they contain a lot of filters. The filters serve to divide up the light into bins of color. So each filter can see only certain ranges of wavelengths, certain ranges of colors within the entire electromagnetic spectrum. So this represents the light that we can see, the colors from violet through red. Remember Roy G. Biv, red, orange, yellow, etc. And the filters can see certain ranges of those colors, even beyond what we can see. So here you see that this filter is into the infrared where we cannot see, and then this is the second camera in Wide Field Camera 3 that's only sensitive to infrared light, and there are numerous filters that are within that camera. So that's how we divide up the light into its component colors. So what do we do to then see these pictures? We're really visualizing this data that the cameras have produced. There's some initial data processing that happens on all the data, whether it's science data or whether we're using that science data to produce pictures. It makes the data consistent from exposure to exposure. So when the astronomers make their measurements, they know those measurements are consistent from time to time. And then we simply translate those numerical values of the light measurements back into brightness on a computer screen or whatever to produce an image. And then finally we composite multiple images taken in multiple filters back into a color image. And then we have what's essentially a photograph. Not essentially, it is a photograph, and we can do all the kinds of adjustments that a photographer would make to make those pictures more presentable. This is an example of the kind of data processing that happens. These are actually the raw images that come from Hubble. And you might wonder why they're so kind of crummy looking. They have all this, looks like they were taken through a snowstorm. Those are actually what are called cosmic rays. They're energetic particles that are all throughout space, and they land on the detector and make these bright spots that we see as bright spots in the image. That seems like a real mess. But fortunately, if we take multiple exposures of the same object, these are identical exposures taken to the same place, we can combine those exposures and magically remove the cosmic rays. We just take the good data and throw out the bad data, and we get a fairly clean image. There's some other artifacts there that are produced by defects in the camera or features in the camera that we can also compensate for by either taking multiple images or doing certain processing on the images. That happens routinely to all the data. So then how do we get these images from the data? we have to scale those intensities from the numerical values into visible brightnesses, from black to white. And again, we're still talking about black and white images here. We have not talked about color at all. So here's one way to scale this image. We see a fairly dark image with some bright spots. Many of those are stars. Some of them are galaxies. If we pick a different kind of scaling, we brighten that. We're essentially cranking up the intensity knob. And now we're seeing a whole bunch of fainter material in between these galaxies. On the other hand, we've also made these, the brightest parts of the galaxy, lost a lot of information in there because it's all gone to white. Fortunately, since these are numbers, we can apply some mathematical processing on these numbers and get the best of both worlds and get all the faint structures and keep all the detail into the brightest parts of the image. A photographer would say we've preserved shadow detail and we've preserved highlight detail, and we have a good range of tonality throughout the whole image. And this is kind of the part that's shading away from the science part of it and shading somewhat towards the art part of this. It's always a combination of science and a little bit of art. So there's a little bit of subjectivity here in how we transform these values, but the goal is always to show as much as possible of what is inherent in the data. As I said, we're seeing the faintest parts of the image and we're also seeing the brightest parts of the image, and that's the goal. We're not trying to pull any wool over anybody's eyes by doing this processing or by doing some subjective processing. We're just trying to show as much of the data as possible. So having said that, I want to emphasize what these pictures are not. They're not colorized, they're not painted by number. The colors don't happen by us saying, oh, I think that pixel should be red, I think that pixel should be green. The colors come out of the data. And they're not really overly manipulated. I mentioned that we have some subjective choices that we make, but I wouldn't say that they're manipulated. We don't do a lot of sophisticated processing like sharpening and things like that you might have access to in a program like Photoshop. We try to keep it as close to the data as possible and honest to the data as close as possible. So where does the color come from? If we use these colored filters and we were able to look through them, we'd see something like this. We'd see red through the red filter, green through the green filter, and blue through the blue filter. What Hubble sees, however, is black and white. So it's these gray, gray, gray. But we know what filter we took that image with. We know the color of that filter. So here's a real world example. Here's that famous Eagle Nebula Pillars of Creation picture. And this is what it would look like what it would look like if we could hold up those filters in front of our eyes behind the telescope and see this magnificent image. These particular filters are very specialized. They are tuned, the colors of these filters are tuned to the emission of colors from particular chemical elements. In this case, sulfur, hydrogen, and oxygen. These chemical elements emit light in particular colors in particular very narrow ranges of wavelengths based on their physical conditions. The density and temperatures that the material is in, the gas that makes this up is in. So these particular emissions are most common in this kind of nebular object. So then, of course, as I said, this is what Hubble sees, gray images from all three filters. But then if we reapply those colors in the computer and composite those together, this is what we get. Now, as you might notice, this doesn't look much like the image we saw before. The color is quite different. And that's because the way we've assigned the colors here is matching the colors of the filters. However, there's another way of applying this, of doing this. If we instead apply the additive primary colors, red, green, and blue, those colors are the ones that add together and combine and produce all the colors that we can see. So every color process, your computer screen, the projector that's projecting these images, your television screen, all produce color in this way. So they have little elements, picture elements on the screen that are either red, green, and blue. The intensity of those going from black to maximum color value combine to produce all the various colors. So if you have more red light coming in, you'll see it as red. If you have more green light, you'll see it as green. If you have a combination of red and green, say, that adds up to yellow. So if you think about all those combinations, then you can produce all the colors that you can see. So in this case, I've made those black and white images using these three primary colors. If we then add those, then combine those together, we get that nice full color image. And I would argue that this is a more valid representation of the image of the object that we're seeing, rather than that pale pinkish version that I had before that was something like what we would see with our eyes if we could look through the Hubble Space Telescope. And I say that it's a more full representation because we're actually seeing more of the physics. We're seeing more of the different kinds of structures that are in this object by using this kind of distilled or stretched color palette. And again, we haven't painted those colors in arbitrarily. The colors fell out of the data. So I'm just describing this to give you a taste of how these color processes work and where the images come from. So then once we have this initial, this is actually the final image after all the manipulations that I didn't want to use that word, all the adjustments that we made to that image. But let me show you what it started out as. This is what it started out as when we first made that color composite from those three color images. So the kinds of things we would want to adjust are the same kinds of things that a photographer might want to adjust in a picture, a raw image they got out of their camera. So you want to adjust the color, you want to make it realistic color, or you want to make it more pleasing color. You want to make it more representative of what you actually saw. You may want to adjust the tonality. So you want nice rich blacks, you want nice clear whites, and a range of tonalities in between. You might want to rotate the image a little bit or crop it to make, again, a more pleasing composition. So photographers always want a nice composition, not only framing in the camera, but after, in post-processing, you might want to adjust that cropping and rotation a little bit to get a more pleasing image. These are all things which I think are not really manipulation, but just making a stronger presentation of that image. And then finally, we do a little bit of retouching or taking out certain artifacts that the camera has put in. For example, there are features such as this little blob up here, which are not real. That's not part of this object. That turns out that it's a reflection within the camera. So these relatively bright stars, the light from those bright stars bounces around inside the camera and causes little reflection ghosts like that occasionally. And I personally see nothing wrong with taking that guy out because it has nothing to do with these wonderful pillars of creation. That's an artifact that the camera produced. We've already taken out some camera artifacts in the routine processing that happened before we got to the color image. So those are the kinds of things we might want to do. There's a couple of other things that we don't need to get too far into that. So I'll just sort of step through, and you can see gradually we're making relatively minor adjustments. And for example, here there's a contrast enhancement. So you get deeper blacks and you get more structure coming out in the image when you've adjusted the contrast. And they're just relatively minor adjustments, a little bit of color adjustment. I wasn't real crazy about that overall green cast, so we shaded it more over to blue, and that contrasts with the yellows and reds to make a richer color palette. And just continuing to make adjustments, and at some point we get to the point where we're happy with it, and then the last step is to crop that image to a nice rectangular presentation that cut off some of the funky edges that happen because of various processing in the camera and so forth. So that's a little overview and a little case study of how we do the images. And I'll just finish up with a little advertising for our site, hubblesite.org, where you can see all the images from Hubble. You can read about what they are, where they came from. You can get a lot of other stuff. We're highlighting the 25th anniversary this year with a lot of different new stuff. There's a whole site devoted to, whole site within the site devoted to the 25th anniversary. If you're a teacher, you can get teaching materials, curriculum materials. If you're a science museum like this one, you can get stuff that's useful for a science museum, all kinds of stuff. So there you have it. So thank you for your attention, and I'll take questions.